let's take a look at section 4.8, linear approximation, error propagation. This video will cover linear approximation. The next one will cover error propagation, or differentials as it's sometimes referred to. Now, a lot of times we wind up using approximations. In mathematics we like to be as specific as possible, but in the practical world we have limits to our measurements, and so we need to use approximations. We use a calculator or a computer, we use approximations. And so we just want to look at a way that we can use calculus to approximate something. Now, again, practically speaking, this is not super helpful because computers and calculators are very, very precise. But this is still a good understanding of how calculus works and how finding the tangent line can be a very good substitute for finding the curve. So the idea is that if we can use the equation of the tangent line to a curve, and if the tangent line is tangent to the curve at a so-called nice point, then we can use a point on that line to approximate a point on the curve, with the hope that they're relatively close to each other. So in other words, we can use the equation, I'll write this out as, well, I really should say we can use the function. L of x equals, and I'll write this out and then I'll explain it in a sec, f of a plus f prime of a times x minus a to approximate f of x near a. Now, what do I really mean? Well, if you notice, if you just call L of x y instead, you'll notice that we're talking about just the equation of a line, the tangent line at the point a comma f of a. So here's an example of what is happening. Suppose I asked you to approximate the cube root of 8.01 as I do above. Right? Approximate the cube root of 8.01. Now, if you think about it, the cube root of 8 is 2. So our answer should be pretty close to 2, 2.0001 or something like that. But without a calculator, we can't really do a whole lot better than that, right? So this is roughly the cube function. This is the graph of the cube root function. Okay, we know that there is a nice point x equals 8. And what do I mean by that? Well, I mean that we know that the cube root of 8 is exactly 2. Right? So we can write down, I'll write over here, f of 8 equals the cube root of 8, which equals 2. Okay? So we can come up with the equation for the tangent line to the curve at that point. And I'll actually just draw the tangent line right there. Right? And this is going to be, let me just write over here, tangent line. And the idea is that this is going to be a pretty good approximation of the cube root of 8.01, right? Now, I'm not going to draw this to scale just for illustrative purposes, but if we're interested in, let me get red back out here, 8.01, and we want to find the cube root of 8.01, note that the actual cube root of 8.01 is right here, but it's not a nice number. Instead, we can use that blue point right there, which is very, very close to the red point. And that is a nice number. That is easily findable because we're finding a point on a line. Lines are easy, curves are hard. So we're going to find the equation of the tangent line, plug in 8.01 to the tangent line, and use that as an approximation for instead of plugging 8.01 into the function. Okay. So how do we do this? Well, first off, we determine our function and our nice points. So we're going to say, oh, you know what? Let's make this thicker. Let f of x equal the cube root of x, which, just to remind you, could also be written as x to the 1/3. Okay. Next up, we, actually, and I should also say, I'll say note that, I guess I'll actually say it like this. Let A equal 8, and note that f of 8 equals 2, right? Because again, it's just the cube root of 8. It's 2, okay? Next up, we find f prime of 8, okay? F prime of 8, now remember, this just means take the derivative, then plug in 8, okay? F prime of 8 is going to be 1/3 x to the negative 2/3. Or you could rewrite this as 1/3 cube root of x squared. And then we just plug in x equals 8. Right, and then this gives us 1/3 times the cube root of 8 squared, which is 1/3 cube root of 64, which is 1/3 times 4, because actually, if you think about it, the cube root of 64 is 4. 4 times 4 times 4 is 64. Right? And then this equals 1/12. Okay? So from all this, we get 1/12. Next up, we set up the linearization, which we call L of x, of fx near a. So the idea is that the linearization, the equation of that tangent line, which equals f of a plus f prime of a times x minus a, this is approximately equal to f of x near a. Now, by the way, how did I get this linearization function? Well, remember that we have y minus y1 equals m times x minus x1, right? And remember that if x1 is a and y1 is f of a, we have y minus, not y1, but we're going to have f of a equals the slope times x minus a. And remember further that when this is the tangent line, the slope of the tangent line by definition is f prime of a. And then if we just solve for y, we get alright? So that's how we're coming up with this linearization function. Okay. So anyway, now we approximate f of x, right? Now we say, okay, so we can say, write it all out here. The cube root of 8.01 equals f of 8.01, right? Which is approximately equal to L of 8.01. All this really means is just plug in 8.01 to the tangent line, and you wind up getting let's see, we're going to get f of a, which we said was 2, right? F of 8, which equals 2. Or maybe I'll just write it out more generally. F of 8 plus f prime of 8 times x minus 8. And this is going to equal 2 plus 1/12 times 8.01, right? That's our x, minus 8. And if you just simplify this out, you wind up getting 2 plus 1/12 times 1/100th, right? 0.01 is 1/100th, right? And this is the same as 2401 over 1200. And we see if you just want to use an online calculator, if we just open up a calculator, right, let's just type in Wolfram Alpha. It's a nice little online calculator. So we can just say, okay, what is the cube root of 8.01 minus 2401 over 1200? See, I figured out what I meant by that. The result is 3.5 or so times 10 to the negative 7. Okay? So it is a very, very, very small error. So this is less than 10 to the negative 6, or 1 over a million, right? So this is an approximation within 1 millionth. Okay? Let's consider another example, right? Here we have, this is a bit more of an applied example, right, that, you see, we could see in population modeling, right? We have a population whose per capita growth rate is 5%, which means that after T years, the growth rate of the population is proportional to the population. It's 5% of the population. Now, it turns out when that happens, that means that the population can be modeled with an exponential function. But what we want to do is we want to approximate the population size after 4.1 years, because exponential functions don't always give nice values. Okay? And suppose we didn't have a calculator or something like that, okay? So the key thing is, right here, population after 4 years is 100. So that gives us the point 4, 100, right? So we don't actually know what f or n of t is. It turns out we could derive it, because this is a relatively simple, what we call differential equation right here. But that's a little above our pay grade. We're not going to do that right now. But we do know that a equals 4 and n of 4 equals 100 because it was given to us. Okay? Now, we're not given n of t, but we still can find n prime of 4, because that's given by dn over dt with, I guess you could say, t equals 4, which means that n equals 100. Right? So, right, this, just to be clear what I mean by this, let me erase the n equals 100 right here. This is going to equal 0.05 times n, which is the same as n of t, right? Just an abbreviation right there. See how I'm just using this right here? Okay? Or, sorry, I said n of t, I meant n of 4. Sorry about that. Okay? And then this is 0.05 times 100, right? Because n of 4 equals 100. And that's going to equal 5. Okay? So we get 5. So then again, we set up the linearization L of x, of f of x, or f of x near a. Now, really, in this case, it's n of t near a, right? I'll call this n of t, n of t. I should have done this here, right? N prime of a, n. All right. So here we're going to have L of t equals, I called it L of x. It really should be L of t in this case. Anyway, sorry. L of t is going to be, remember, just by definition, it's going to be n of 4 plus n prime of 4 times t minus 4, which in this case is going to be 100 plus 5 times t minus 4. Okay? So then we approximate n of t, and we say, okay, n of t approximately equals L of t near 4. So we can say n of 4.1, right? I did say 4.1, right? Yeah. Oh, and that should be 4.1. That's a typo. L of 4.1, which equals 100 plus 5, times 4.1 minus 4, and that's going to give us 100 plus 5 times 0.1, and that's going to give us 100.5. Now, I just want to emphasize, sometimes when a problem is really complicated, you don't want to simplify. With these problems, the whole point of it is getting a nice answer, so you always have to simplify as much as you can. Right? Now, it turns out we know that n of t winds up equaling e to the 0.05 t. I suppose there could be some kind of a coefficient there, but suppose there's not. Anyway, using Wolfram Alpha, let's just see how close our model is in this case. Here we have 100.5 minus e to the 0.05 times 4.1. See what that gives us. Hold on a sec. I think I may have. Is this e to the 4.5? I'm just wondering why that's a little bit high like that. I guess that was a little bit further off than I realized. But let's see. We have that. I want to make sure that this is all correct. 0.05. So oh, you know what? I think I'm missing the fact that the population after 4 years is 100. So we have a data point, so we actually could solve for a coefficient there, I think. Let me just see one sec. What is, on a sec, e raised to the 0.05 times 4 times 4. That's going to give 1.2. So I'm going to say 100 divided by 1.22. Okay, so that's our coefficient. Okay. So let me just put this here. We actually know a little bit more. Turns out our function is really 100 divided by 1.22, or roughly speaking, times e to the 0.05t. Right, now we'll get a much better approximation. So anyway, now we go back to Wolfram Alpha. And this is times e raised to the 0.05 times. Oh no, sorry, we already multiplied it by that. Minus 100.5. There you go. So it's actually a decent approximation. It's not amazing, but it's pretty good. Right? So we see that minus 100.5. Oh, sorry, this is this guy here. Minus 100.5 is less than 0.4. So this is an okay approximation. Still pretty good. Still pretty good. Right. So we have these two approximations, okay? Let's just quickly do two more, okay? So here, we're trying to estimate this guy. You have to find your function, find your nice value. Let f of x equal x to the 4th, right? Because that's what's happening here. And let a equal 2. So f of 2 equals 2 to the 4th, which equals 16. Okay? F prime of 2 is going to equal 4x cubed, and then we plug in 2. This gives 4 times 2 cubed, which equals 32. And so then we say, okay, the linearization of this guy is going to be f of 2 plus f prime of 2 times x minus 2, right? Which is going to be 16 plus, what is this going to be, 32 times x minus 2, okay? And then all we do is we say, okay, 1.999 to the 4th approximately equals L of 1.999, which equals 16 plus 32 times 1.999 minus 2. And note that unlike the other two times, we're actually getting a number that's negative in here. This is negative 0.001, right? So this winds up being 15.968, I think it is. Okay? Which makes sense because a number a little bit less than 2 to the fourth power should be a little less than 16. Okay? One more example, example 4. Same sort of situation, except the per capita growth rate is 3%, right, given by this guy. And we also know that this is true, right? So here we have n of t equals, well, we don't actually know, but we know that n of 7 equals 350. And further, we know that n prime of 7 equals dn over dt, plugging in t equals 7, which gives 0.03 times n of 7, which equals 0.03 times 350. And we can do that one out. I think that's going to be it's going to be what, 1,050. That's going to be 10.5. Is that right? I think. Yeah, I think that's right. 10.5. Okay. So our linearization is going to equal 350 plus 10.5 times t minus 7. So n of 7.3, right, the population after 7.3 years is going to approximately equal 350 plus 10.5 times 7.3 minus 7. Let's see how well we can do this, right? It's going to be 350 plus 10.5 times 0.3. And this is going to be 350 plus, what is that going to be? 105 times 3 is 415. 4.15. This is going to be 354.15. Do they give us units? They don't actually give us units. So we'll just stop there.